So yeah, thank you for the presentation. I'm glad to speak here. Actually, this is my first conference ever, so I'm a little bit nervous. So please root for me. Thank you. So yeah, I'm going to talk about the size of Bruhat intervals, and the results I'm going to show in the context of affine-Weil groups were obtained in collaboration with Castillo, Levinsky, and Plaza. So I will go quickly through the definition of Bruhat intervals. So we start with a Coxeter system WS. We have a length function on the group. So you define the length of an element as the minimal amount of generators that you need to grade it. This is called a reduced expression. And we also have a partial order in the group in which we say an element U is below W if for each reduced expression of W that you take, you can delete some generator from it to obtain a reduced expression of the element below. So this is called the strong Bruhat order. And from it, we can take general intervals. So I use the usual notation. And as for lower intervals, where am I? I write less or equal than W to mean all the elements below it. So what about these intervals? What about their cardinalities? So for general Coxeter systems and general intervals, whenever the interval has length 2, then it has precisely 4 elements. As you can see, this is the Hasse diagram of the interval. So smaller length intervals are, well, not interesting. And you have Coxeter systems where even length 3 intervals are not bounded. We have a result by O, Postnikov, and U. And they work in the symmetric group and for smooth elements, meaning that the corresponding sugar variety is smooth. And they compute the cardinality of their lower Bruhat intervals as the number of chambers in a hyperplane arrangement corresponding to this element. So it actually was conjectured in this paper that this should remain true not only for the symmetric group, but for the whole finite Weil groups, which was proven. So this was actually submitted for FPSAC, I think. But for us, in our collaboration, our starting point and motivation was a paper by Levinsky and Patimo. So they worked in a affine type A2 tilde, and they computed all lower intervals and their cardinalities. And under some parameterization of the group, these formulas are polynomial formulas. And they were actually trying to compute all the Cauchy-Lustig polynomials in this affine type. And there is a special technique in the Hecke algebra that needs this information of the cardinalities of the lower intervals. And well, it's necessary, it's not sufficient. So in particular, they compute all Cauchy-Lustig polynomials. And similarly, we have a paper by Battistelli, Bingham, and Plaza in the same year, where this time they work in affine type B2 tilde. They use the same techniques. They also compute almost all Cauchy-Lustig polynomials in this affine type. So they had to compute all lower intervals, their cardinalities, and they also got polynomial formulas. So the results I'm going to show will generalize for all affine Weil groups, all affine types. And we will recover some of these polynomial formulas. And the first result, we call it the lattice formula. So this result relates lower Bruhat intervals with lattice points in convex polytopes. So I will need to define which lower intervals, which convex polytopes, which lattices. And I will do this in this affine type of A2 tilde. So here we have the plane. We have the root system of type A2. It has 6 roots. I'm sorry. So yeah. So the red arrow is the simple, the red and the blue arrows are the simple roots. The green arrow is the highest root. And then we will define an affine Weil group, and this will be in bijection with the set of equilateral triangles here tessellating the plane. So how do we do this? First, we take the orthogonal lines to these simple roots. These are the red and blue lines. And the green line is orthogonal to the highest root, and then we shift it by -1. And these three lines make up a triangle, and this triangle will correspond to the identity element of our group. And then the affine-bile group is the group generated by the reflections along these three lines. So if you can see that if you try to reflect this identity triangle through these three lines, you start to get the tessellation of the plane. And this action actually is simply transitive, from which we identify this set of equilateral triangles with our affine-bile group of type A2 tilde. So this is the affine-bile group. We also have the finite-bile group, which attached to this root system, which is the subgroup generated only by the red and the blue reflections. So this is the finite-bile group. It has 6 elements. It has a maximal element W0. It is maximal both in length and in the Bruhat order. And note that you can see that you can define this group as the triangles that are precisely adjacent to the origin of the plane. So this is the finite-bile group. So the first lattice we consider is the root lattice. It is the set of green dots, so it is spanned by the simple roots. And this lattice is contained in the weight lattice. So we take the dual basis of the simple co-roots. These are the fundamental weights. And these guys span a lattice called the weight lattice, which are all these white dots. So in general, the root lattice is contained in the weight lattice as a subgroup of finite index. And in our case, this index is 3. So here we're looking at the quotient. So you can see, so you have the root lattice inside this weight lattice. This is the green lattice. And then you have 2 translations of it, namely the blue lattice and the red lattice. So we will be working with these 3 lattices. And the main protagonists of this talk are these special elements in affine-bile groups. So these are the elements here highlighted in gray. So in this example, it's quite easy to draw these elements, but how do we define them in general? So the first special element is always the maximal element of the finite-bile group, and then we take translations of it by dominant weights. So the dominant weights are all the white dots you're seeing, and those are the weights lying in the cone of the fundamental weights. So you take any dominant weight, that is any white dot, for example, this one. You take your W0 triangle, and then you translate this by your dominant weight. And in this way, you obtain all your special elements. So these special elements, we call them theta elements, and they are indexed by dominant weights. So if you take a dominant weight lambda, you have the corresponding theta element, theta of lambda. So we will be working with the lower intervals of these guys. And this is the picture you have to have in mind. So this is the lower interval of this theta element. So every element in the affine-bile group of type A2 tilde that is below our theta element is represented here by a gray triangle. And as I said, the lattice formula can describe this interval, this lower interval, in terms of lattice points in a convex polytope. So which convex polytope is quite easy to define. So back to our dominant weight lambda. In this case, it was a blue weight. So whenever you take the orbit of this blue weight under the finite-bile group, you get a blue orbit. And then you take its convex envelope, and we arrive to a convex polytope P. In general, this is just the permutohedron. In this case, is not regular. And since the lattice here playing a role is the blue lattice, we will take blue lattice points inside this permutohedron. So here we have the whole picture. We have our theta element, its lower interval in gray, its corresponding permutohedron, and the lattice points in this permutohedron. So these are the blue dots. And with this, we can describe the interval, noting that so around each blue dot, you have precisely 6 triangles. And the union of such triangles is precisely the whole interval. So in fact, each one of these blue hexagons are just translations of the finite-bile group. And if we want to know how many elements this lower interval has, well, that is how many gray triangles we have in the picture. We just count the numbers of blue points, and then we multiply that by 6, the order of the finite Bell group. So this is the lattice formula. I hope it's clear. And it works precisely the same for all affine Bell groups. So for any irreducible root system, you have the same definitions. You have your permutohedron, your theta elements, and so on. And this is the general statement of the lattice formula. So we can describe the alcoves of the lower interval of a theta element. So in our case, the alcoves were triangles, as translations of the alcoves of the finite Bell group. And these translations are the lattice points in the corresponding permutohedron of our theta element. And if you take this equation and you count how many alcoves you have in each side, well, you get this equation in the bottom quite easily. So the cardinality of our interval becomes the order of the finite Bell group times the number of lattice points, as in the previous example. So you may have realized that here we have just built a bridge between Coxeter combinatorics and convex geometry. So what we did is that we used this lattice formula and the machinery coming from convex geometry to compute these lattice points. We mainly used techniques developed by Berlin-Berg. And we count these lattice points to derive a closed formula for the size of our interval. So this leads, yes?
Can you recall what is this theta of lambda? Which particular element?
So lambda is, I'm sorry, it's the other way around. Spoilers.
Okay, I see.
Yes. So yes, so you have your dominant weight to this. You can associate any theta. In this, exactly that, yes. Yes, so in general, so here, okay, so with question, so in type A, it is self-dual, so the root lattice is the same as the co-root lattice. But in general, you should work with the co-roots and with the co-weights. But if you, yes, so here I'm identifying the space with its dual. You should probably not do that, but there's no deep reason behind it. So yes, so okay, so this will lead us to our most powerful result, the geometric formula. So I don't have the time to explain how this counting of lattice points works. It's quite technical, but what I can do is show you how this geometric formula will work for our beloved example of A2 tilde. So I'm going to do a seemingly pretty weird construction, so please follow me for some slides. I hope it will be clear soon. So back to our permutohedron, we have the corresponding dominant weight lambda. So first, I'm going to define some faces of the permutohedron. Namely, the red edge, I will call it F1. The blue edge, I will call it F2. F12 is the whole polytope as a face of itself. And F empty set is the vertex lambda. So I have defined 4 faces of this permutohedron, which are the faces adjacent to my dominant weight. This is one step. On the other hand, you have this partition of the plane. You can always do this. One part is your convex polytope. Then you go orthogonally away using its phase structure. And from this, we have a partition of the alcoves of our interval. OK? So regarding the cardinality of this interval, as we saw, it's just the number of colored triangles. That is, if we take the area of this figure and we divide it by the area of any triangle, we have the size of our interval. So we can do this, but color by color. And we will arrive to a formula looking like this. So the size of our interval is some number times the area of the yellow part, plus some number times the length of the red edge, F1. So this term in the sum, this term, represents the area of the red part divided by the area of any triangle, plus some coefficient times the length of the blue edge, this is the blue part, and so on. OK, so this is the construction. What about this construction? The whole point of it, well, you can do this for any theta element. So if you take another theta element, this implies that you take another permutohedron. So you have that these areas and these lengths will change. However, for some magical reason, these mu coefficients won't change. So they have the property of being independent of your choice of theta element. OK? So in general, these areas and lengths are volumes of the corresponding dimension of the faces of the permutohedron. So they denote them by V. And this we call the geometric formula. Yes?
So you mean the last one?
Yes, so you will soon see I did not normalized. I just take, so I.
Like the edges is the lattice line, the edges.
No, it's you, so.
It's not?
So you can normalize as you want. There is no problem. However, these coefficients will change according to your normalization. But here, so clearly, this edge F1 depends on the simple root alpha 1. And you can compute it just using its norm. But yes. So this I call the geometric formula. Any linear combination, I mean, when you have this size of your interval becoming this linear combination of the volumes with coefficients satisfying this property. So these volumes have been studied, for example, by Postnikov, and they're quite nice. And if you take coordinates of your dominant weight, you can see that here on the left, these polynomials become, these volumes become polynomials. So as for the equation, don't worry about these roots. I did not normalize these volumes, no deep reason behind it. And on the right-hand side, you can see that these coefficients do not depend on your choice of theta element. That is, they do not depend on your dominant weight. If you take all this information and you put it back into the geometric formula, what you will get is that the cardinality of this family of lower intervals becomes a quite nice polynomial. So as promised, this worked in complete generality. So for any irreducible root system, you have your affine group, and this is the general statement. So the cardinality of the lower interval of a theta element becomes a linear combination of the volumes of the faces of the permutohedron corresponding to our theta element. So these are the V's here. And these coefficients is really important. I stress this once more. They do not depend on your choice of theta element. If these coefficients were to depend on your choice of theta element, this formula is completely trivial. So that's the important part. And once you know that they have this property, you can show that they are actually unique with this property. So for every irreducible root system, for every affine group, you have a unique geometric formula. And as in the example, taking coordinates for your dominant weights makes that these volumes are polynomials. So the cardinality of your intervals also become polynomials. OK, so this is the general statement of the geometric formula. And you can see that here we have computed our interval in terms of some quite easy to compute volumes, polynomials, and some numbers. So what about these numbers? Well, we know how to compute in complete generality only 2 of them. In type A, we know how to compute a lot of them. We have closed formulas for them, not all of them, but a lot. You can see them at the end of the extended abstract. But regardless, if you fix an irreducible root system, you can always compute these coefficients, for example, by some system of equations, by computing some lower intervals of some small thetas. And once you have your coefficients, you have your polynomial. And if you have your polynomial, you can compute for any theta you want. So here the point is that the problem of computing these lower intervals in affine groups is a doable problem. And at least for these elements, it is clearly controlled by convex geometry. But we have strong evidence that there are similar formulas for the whole group, not only the theta elements, but of course, these mu coefficients will change according to your theta element, according to the elements you take in the group. So, OK, this is the general statement. And as a final remark, I just want to say that I lied to you. So, Yeah, so think about it this way. For every irreducible root system, we know that there is a geometric formula. And this is the formula above. And you know that you have this drawing of your partition of the alcoves of the corresponding interval of these theta elements. So for every affine-Weil group, we have the geometric formula and the drawing. In the A2 tilde case, we derived this formula from this drawing. And you can do the same thing in A3 tilde, but from A4 tilde and so on, they do not coincide. You have the both things, but they sadly don't coincide. What's misleading also is that here in this example, the permutohedron, the yellow part, is completely contained in the alcoves of the interval. So the yellow part is completely inside the interval. This is not true in general also. So this permutohedron is being punctured by these zigzag lines of this interval. And as if this wasn't bad enough, we have strong evidence that, not evidence, we know that in A24 tilde, there is a negative mu coefficient. So the remark here is that we were completely shocked that the intuition leading us to this geometric formula is completely wrong, falls apart all the time. But for some reason, the geometric formula works for all affine Weil groups. Thank you for your time.
All right. Are there any questions?
Were you going to comment at all on other intervals with some bottom knot the identity?
Oh, okay, good question. So, yes, in our collaboration, our program is to compute all intervals in affine Weil groups. So we started with these elements, these theta for lower intervals and these theta elements. They have quite nice algebraic properties. They are maximal in some double cosets. So using this, we had the lattice formula from which we could compute this. But this is the starting point. Then we want to compute intervals going from thetas to thetas. So what you can do is that your interval, you can decompose it as the lower interval of the end on the right, minus the elements that are not greater than the elements on the left. And this not greater element set has a quite nice geometric description. So it is a kind of, so if you look from far away this interval, it is kind of the permutohedron. It looks quite a lot like it. And if you look from far above these not greater than sets, they look like stars. So the interval is like taking your permutohedron and subtracting some star. And yes, but this is ongoing. So this will be the first step. And then you can, so these theta elements are general enough that they are forcing their properties to the whole group. That's the idea. So those are the steps. Yes?
Over here.
Sorry, just a quick one. Have you considered twisted Bruhat orders?
Can you repeat, please?
Have you considered twisted Bruhat orders?
Twisted, I'm not familiar with that. Maybe we can talk about it later.
Sure.
But
All right, Sam, you had a question? Or
Have you thought about plugging negative numbers in for like some combinatorial reciprocity things as well?
in the polynomial?
Correct.
Yes, I've tried to amuse myself, but so yeah, I've just tried the polynomial. Of course, as you know, exists. So it makes sense in terms of the volumes. So you have linear combination of these volumes, and they are polynomials. You don't need them. So you don't need for the volume to. So this volume doesn't need lambda to be dominant weight. It can be any point in the plane. So that is one explanation, but no more than that. I have not done more than that.
okay, one more
Yeah.
question, Frank.
I'll ask one of the two questions I had. This one's so your formula you showed us, and also it seems to be true for A2 from thinking about it, is an integer polynomial with non-negative coefficients. Is that always the case? You have an integer result, and so it's unusual if the coefficients are all integers.
So no, it's not. That's what I said at the end. It's not true. These coefficients, there is a negative mu coefficient in A24.
No, I'm not talking about the mu coefficients. You wrote down your polynomial in something in terms of parameters. It's an integer polynomial. I mean, it takes integer values. In this case, you have positive integer coefficients. Is that always the case?
That's a really good question. We actually think about this like 2 weeks ago, and we don't know why. I have computed this up to, in type A, up to A7 tilde, and it is the case, but I don't know why.
Okay, one more question.
It's a related question on this example. It's a symmetric polynomial. Is that a coincidence or something? Because it makes sense for A larger than B in your geometric interpretation.
So I think your question is more about more than the polynomials here. Is the polynomials here on the left, the volumes? So in fact, this is so these volumes have quite nice interpretations, and well, I don't recall that much. So Postnikov has some results of it. You can read about it. It has a lot in type A. But what is true from these volumes going to this polynomial is the observation that, so the volume 1, 2 is always giving you the homogeneous part of degree 2. The volume 1 and the volume 2 is giving you the homogeneous part of degree 1. And this will be always be the case in general.
But I mean, the final count is symmetric in A and B.
Yes. Yes. So this is because yes. So it's because I think the volumes have this property, but I don't think it is true in general. So in type B, it's not true. For some volumes, it will be. For the whole polynomial, it won't be. So my partial answer is in type A, yes.
Thank you.
You're welcome.
The two simple roots are symmetric. So maybe in A3 tilde, you have the root in the middle has different properties than the two in the borders.
Mm-hmm.
So I'm not sure if this is the reason or is a type A reason.
I have to think about it. But I think
but
it's
this
a type.
is super symmetric because A2
Yeah.
tilde, the two roots are symmetric. So
Yeah.
you expect a symmetry in the formula.
Okay, all right. Thank you for all the questions, and thank you for the wonderful talk.